51. What's the relationship between the two species shown below? Okay, if you know the isomers, or three different types of isomers, you can eliminate A, B, and D. The isomers they have the same compound, just like you see the N2O and N2O, but they have a different arrangement of atoms. However, in the diagram shown here, we don't see the different arrangement of atoms. We see NNO and NNO. Had it been the NON, then it would have been the structural isomers. Well, the geometric isomers tend to have this kind of form. Normally you have double bond, and then we have cis and trans. So when we have both chlorine or something electronegative on both sides, then we have a cis geometric isomer. And then the trans isomers are the ones that are on the opposite side. For example, I can draw, okay, I still have a 2 carbon, 2 hydrogen, and 2 chlorine, but this time I have the opposite location for the chlorine. Okay, the net dipole for this trans will be 0, whereas the cis has toward the chlorine side. So that's geometric isomers, something you're gonna definitely learn in organic chemistry. And enantiomers also very heavily the organic chemistry material, and then later on you will learn something like chirality, and then the Kahn-Ingold and Prudhoe like priority system, the RS configuration, and all that. Well, to make it simple, these are the isomers that have a mirror-like image. So for example, when you have a right-hand globe and the left-hand globe, you cannot really fit the left-hand globe on your right hand, well, unless you really flip it out, but other than that you can't. So those are the enantiomers. Like it's like a mirror image that cannot be superimposed to each other. And then the structural isomers is the most simple. It's the most simple one that have the same chemical formula, but have different position, or they are just arranged. The atoms are arranged in different order. So that's the structural isomers. Now this is specifically resonance, because we don't change the order of atoms. It's just that a pair of electrons is moving around. So let me demonstrate that. To move from the left structure to the right one, I just have to move this lone pair and then assign it between 2 nitrogen atoms, and then that's gonna cause one bond pair between N and O, because I cannot form 5 different bonds around the central nitrogen, and that's how you form that. And to go from left to right, right to left, all I have to do is just move this lone pair, the bond pair toward the bond between nitrogen and oxygen. Okay, so answer to 51 is C. 52. If A represents the central atom, in which molecule is the FAF angle the smallest? Well, let's start with A, boron trifluoride. When you draw the boron trifluoride, you will notice that only 3 pair of bonds are present, because boron only has 3 valence electrons, and it's very tiny, and they don't have to follow the octet rule. So we have sp2 configuration, or the hybridization, and that's always corresponding with 120 degrees between the FBF bond angle here, or FAF, based on the given direction, and that happens to all of them. Okay, they all become 120 degrees, and think like it's on a page or on a plane, and that's why we call it trigonoplanar geometric shape. So that was A. That's already 120 degrees. Now if you take a look at the carbon tetrafluoride in choice B, it's gonna be tetrahedral. So what it means is I'm gonna draw the wedge dash shape. meaning when you see the wedge here, it's like a popping out of our plane or fluorine, and then the simple lines are embedded on like a page. So you can kind of see that the bond angle between the carbon and fluorine, carbon, fluorine will be 109.5 degrees. So far, the comparing A and B is much better because we want to find the smallest bond angle. Now let's take a look at the NF3. I have a lone pair, and then I have trigonal pyramidal shape. The general rule is when you have a I just drew the lone pairs around fluorine. When you have a lone pair above the nitrogen, it's gonna kind of push. There will be electron repulsion between this and then the bond and the lone pairs here. So it's gonna kind of push the angle, and this angle is no longer 109.5. It's more like 107 degrees. If you try to use the NH3, the very original example you see in the textbook. However, we have fluorine, which is very electronegative. So a lot of the all the bond pair, the electrons are going to be more shifted toward the fluorine. So it's going to really create a smaller bond angle compared to the tetrahedral, symmetric tetrahedral shape that we just saw in choice B. So we expect this to be less than 109.5 degrees. And then finally we have oxygen difluoride. Now we're just gonna show you that now I have a two lone pair above the oxygen, so it's gonna push more. It's gonna push the angle between the fluorine and oxygen and fluorine, and if you use a water analogy, it's gonna be like less than 105 degrees. However, when I checked the online, when I googled it, it turned out to be 102 degrees for the nitrogen trifluoride as opposed to the oxygen difluoride. The oxygen difluoride in Google was like 103 degrees. That was kind of funny one because and then this was like 102.1. So technically, I'm pretty sure C is better. C is the right answer. However, if you just use the general rule, like the very exemplary models, like nitrogen, no, ammonia, and water, and you notice that D is D would be the answer. So either C and D can be answered. But then answer key said D is the answer. Alright, so moving on. Where is it? 53. On the basis of Vesper theory, what geometry is predicted for the central sulfur atom in SOCl2? Okay, let's draw this. Okay, we already know that sulfur is the center, and then we have oxygen and chlorine. Okay, so let's actually add the ordered valence electron. Sulfur has 6, and oxygen has 6. Chlorine has 7, but we have 2 of them, so you have to multiply it. So when you add them up, you're gonna get 26 total valence electron. Okay, it's a valence electron, not total electron. So we can first form single bonds for the given atoms. Alright, so six electrons are already used up for bonding. That leaves us only 20 valence electron for lone pairs, and that makes sense when you just distribute the electrons, okay, like that. So what is this shape? Well, it's trigonal pyramidal, just like the one we saw with the nitrogen fluoride, nitrogen trifluoride. We have a lone pair, and then we have like a trigonal pyramidal shape on the below. So the answer is D. Alright. 54. How many sigma and pi bonds are in a molecule of ethine? Okay, ethynes are alkynes. These are hydrocarbons that have triple bond. So this is how it looks like. And you have 180 degrees of bond angles, and it's a linear geometric shape. Alright. So anytime you see a single bond, you have a sigma bond. So I have one. Okay, when you see triple bonds, still use one of the three to be the single bond, and then so I have a total of 3 sigma bonds, like 1, 2, 3. Now the second and third bond between carbon and carbon, our triple bond, is going to be attributed to the pi bond. So we have 2 pi bonds. Okay. So the answer is D. 55. What's the number of structural isomers with the molecular formula for our hexane? Well, let's try them. The easiest way is we can have like that. 1, 2, 3, 4, 5, 6. You have a hexane. I'm not in this shape. I'm not writing the hydrogen, and that's very time consuming. If you really want, you can even try like this. Okay. In fact, most people at this level may not be really comfortable with this notation, so I won't write the whole carbon stuff. Okay, I'm not gonna write the hydrogen because that's gonna be really taking long. So you just gotta be able to distribute the hydrogen based on your knowledge. And so that's one form, and the second form is we can form the branch. So I have 5, and I can have a substituent on the second carbon, and I can also have here. Now if I make a force, the same shape as this form, so I'm not doing that. Yeah, I'm not having a unique shape. So far I have 3, right? 1, 2, 3. Let's see if we can form more. I can form this. Okay. And I can also form this way. Anything else will be the one of this shape. So the answer to 55 is C, 5.